Hi everyone, so today we're going to go ahead and continue with our chapter 3 notes. And today we're going to go ahead and start by talking about rotations. So when we talk about rotations as a transformation, we also have to talk about the center of rotation. And the center of rotation is a point in which a plane figure rotates around. So it's sort of like how the Earth rotates around the sun. So the sun is our center of rotation, and we are the object that is then rotating. It's still Earth, nothing changes about it except its location in correspondence to the actual sun itself. We also have to talk about an angle of rotation, and an angle of rotation is an angle measurement by which a figure rotates. So for example 1, I'm going to show you the process on how we would construct a rotation when given an object, the center of rotation, and the given angle measurement. Again, we're just going to use example 2 as an additional practice problem for you. I just want you to understand the process because these are not questions that would show up on a quiz or a test, but you do need to be able to identify it and identify how you would create that in case it did show up on a district final. So for example 1A, it says that we're rotating 65 degrees. And in this case, it doesn't actually tell you which direction. So if the question doesn't tell you which direction to rotate, we're always going to be using counterclockwise. And we do that because our quadrants are actually labeled counterclockwise. So on part A, it says that we are rotating 65 degrees, and it looks like point K here is my center of rotation. So if I'm going counterclockwise, I would start with point R, and I want to go 65 degrees. Okay, so I would want to use a protractor to do this. I know that going straight up and down would be 90, so this is going to be an acute rotation. So based on this, I'm going to rotate this point 65 degrees counterclockwise. Okay, that distance from K should still be the same. So from R to R prime, I could see that from R to K should be congruent as it is R to R prime. This is what keeps it the same shape. We would then do the same thing with our T. So I want to rotate my T, and sorry, I do apologize, we should be going counterclockwise, so I moved my R in the wrong direction. Okay, so that would have been clockwise, I should be going counterclockwise, 65 degrees. So this should create a 65-degree angle between your R and your R prime. Okay, we would do the same thing with RS, rotating it 65 degrees counterclockwise. And we would want to make sure that from K to S and from K to S prime would be congruent measures. And then we would do the same thing with our T, moving it 65 degrees to get our new point of T prime. Okay, and then lastly, we would connect all of those to recreate our image from our pre-image. So in this question, part B is just going to be extra practice for you, whether you want to use it as extra practice of using a protractor, or if you just wanted to use it as additional practice for studying for the test. So let's focus on rotations in a coordinate plane. So all of these rotations within the coordinate plane only apply when you're rotating around the origin. And the origin on a graph, again, is 0, 0. So these rules specifically apply when I rotate around that origin. So if I'm rotating 90 degrees counterclockwise, your x and your y coordinates switch, and your y switches signs. And that's because I'm moving coordinates almost diagonally. Okay, 180-degree rotation, it's like flipping it over a line. Okay, but in this case, our rule for rotation, because we're going counterclockwise, is going to be negative x, negative y. So the only thing that changes is the signs on your x coordinate and the signs on your y coordinate, but they do not switch positions from one another. And then the 270-degree rotation, counterclockwise, your x and your y do switch. And in this case, your x coordinate negates before switching to that second coordinate. These rules will not be given to you on the test, as they are not given to you on the district final. So these are rules that you will need to memorize. So I like to think of it as switch, no switch, switch. And then it's a pattern where it's the first one that gets negated and then the second one that gets negated. So these are rules that you do need to memorize for your chapter test. So for example 2, it says you have a parallelogram FGHJ. So we're going to go ahead and start by graphing our original figure. So F is at 2, 1. G is at 7, 1. H is at 6, negative 3. And J is at 1, negative 3. So we have our pre-image before we've done anything about it. So example 2 says I want to graph that image and the image after a rotation of 90 degrees about the origin. So I'm rotating around the origin, which means all of the rules for the coordinate plane work for us. It doesn't tell me a direction, so if it doesn't tell me a direction, we're going counterclockwise. The only time that we're going clockwise is when they indicate that it needs to go clockwise. And the reason why is because our quadrants in our graph go counterclockwise. Your first quadrant is actually your top right. Your second quadrant is the top left. Your third quadrant is the bottom left. And your fourth quadrant is the bottom right. So because your quadrants are all counterclockwise, we move our coordinate points counterclockwise unless told otherwise. We're going with the natural flow of the coordinate plane. So if I'm going 90 degrees about the origin, the rule for 90 degrees counterclockwise around the origin is that my x and my y are going to switch, and that first coordinate is going to change signs, which means that my f prime, your x and your y flip. Okay, so it was 2, 1 before. My y coordinate was 2. Sorry, my x coordinate was 2, which makes my new y coordinate 2. And my x coordinate becomes a 1. And then that first number switches its sign. So my f prime is going to be at negative 1, positive 2. Our g prime coordinate, it was 7, 1 before. So since my y coordinate was 1, this is our new x coordinate. Our x coordinate was 7, so this is our new y coordinate. And then we are going to negate that first coordinate. So we have a point at negative 1, positive 7. H prime, our y coordinate was negative 3. So that's our new x coordinate. And our x coordinate was 6, so that becomes our new y coordinate. And then the sign on the first one needs to flip. So now our new h prime coordinate here is going to be at 3, 6. And lastly, our j prime coordinate, your y coordinate was negative 3, so that's now our x coordinate. And 1 was my x coordinate, so that is now my y coordinate. And we are going to switch the sign on our x coordinate, our new x coordinate. So we have our j prime being at 3, 1. And I just double check. My image rotated this direction, which is in fact counterclockwise. And then I double check I used the right rule, and I did. So this is going to be our image and our pre-image. Using these rules, I want you to go ahead and pause this video and try example number 3. So on example number 3, we're going to start by graphing our pre-image. So D is at -4, 3. E is at 1, 2. And F is at -3, -3. So here is our pre-image before we have done anything to it. And this time we're rotating the image 180 degrees. It doesn't tell me where, so it means that I am going to rotate around the origin. And since it's 180 degrees and it doesn't tell me a direction, I should be going counterclockwise. So I'm using the rule that was provided to me. I know that at 180 degrees, my x and my y coordinate will not flip at all. They will remain in the same location, but the signs on them will switch. So my D prime, my x and y coordinate, I had a -4 and a +3. Based on this rule, I need to switch both of these coordinates, so I should have a new point at 4, -3. So this is now D prime. My E prime, I get by looking at the E coordinate, which was 1, 2. And based on this rule, both signs on that need to flip. So my new E prime is going to be at -1, -2. And F prime. F was -3, -3. If I'm going to switch the signs on those based on this rule, my new F coordinate is going to be at 3, 3. And you will notice that based on our rule, they've actually switched diagonally of their coordinates of one another. So D was in quadrant 2, and my D prime is in quadrant 4. So 180 degrees is a direct reflection over that origin. So this is how we rotate around the origin. Now, this is formal geometry, so things get a little challenging sometimes. So we always want the luxury of rotating around 0, 0, but that doesn't always happen for us. So we also need to talk about how to rotate around a point that's not the origin. So the first step in doing that is to use the point of rotation as a translation vector. So it's like moving your coordinate point or adjusting your points as if they were going to the origin. We're then going to use the rules of rotation to rotate our figure, and then we're going to move our figure back. So let's look at an example so we can try to explain this a little bit better. So on example 4, we're going to start by graphing our pre-image. So I know that R is at 1, -3. S is at 3, -4. And T is at 1, -7. So here is my pre-image. I have done nothing to it yet. So we want to rotate triangle RST 270 degrees around the point 2, -2. So our rules of rotation only apply at 0, 0. So the first thing we need to do is modify our equation for ourselves. So in order to get from the point that they want us to rotate around to 0, 0, I need to figure out the translation vector that would get that point there. So my x-coordinate changes 1, 2 to the left, so that makes it negative. And once I moved to the left 2, I would need to go up 2 to get to 0, 0. So if you notice, this is the complete opposite of the point that they gave me. They gave me positive 2, negative 2, and our translation vector is a negative 2, positive 2. This will always hold true, where it's flipping the sign to create that translation vector. So if I'm starting with these coordinates of r being 1, negative 3, s being 3, negative 4, and our t being 1, negative 7, I have to apply this translation vector before I can use the rule, because it would take moving all of these points to the left 2 and up 2 in order for that rule to take place. So I'm going to apply this translation vector like we talked about last lesson. So I'm going to subtract 2 from all of their x coordinates. So 1 plus a negative 2 is negative 1. 3 plus a negative 2 is a positive 1. And 1 plus a negative 2 is a negative 1. All of my y coordinates of those starting points are going to be moved up 2. So negative 3 plus 2 is going to give me negative 1. Negative 4 plus 2 is going to give me a negative 2. And negative 7 plus 2 is going to give me negative 5. So these are the points that I can use now with the rule, because the rule applied at 0, 0. So now I moved all of my points, including the point I'm rotating around, and all of the points I am rotating, so that I can make that rule possible. So the rule for a 270-degree rotation, I know that my x and my y flip, and that my second coordinate is going to change its sign. So now we are using this rule for 270 degrees using these new points that we just used. So for r, when I moved it, I got negative 1, negative 1. And I'm going to apply that rule of 270 degrees. So my x and my y flip. And then that second coordinate is going to change signs. For s, your x and your y flip. And your second coordinate changes signs. For t, we're following the same process. Our x and our y flip, they switch positions, and our second coordinate is going to change signs. So even though before, when we used the rule, that came to our final answer, here it's a little bit different. And the reason why is because we had to move our coordinates in order to use the rule. So because I moved those coordinates so that the rule applied, I now have to move those coordinates back. So your translation vector that you used here in step 1, you have to do the opposite in step 3 to get your final answer. So since I moved all of my x's to the left 2, I now need to move them all to the right 2. Since I moved all of my y's up 2, I now need to move them all down 2 so that they're back in their original positions. And this is what's going to give us our final points. So I'm using the coordinates that I used from the rule. So my r, after I moved it, rotated it, now I'm moving it back. Negative 1 plus 2 is going to give me a positive 1. So I'm adding 2 to all of those x coordinates that I found in step 2. Negative 2 plus 2 is going to give me 0. And negative 5 plus 2 is going to give me a negative 3. For your y coordinates, we need to move them back down 2. So positive 1 plus a negative 2 is going to give me negative 1. Negative 1 plus a negative 2 is going to give me negative 3. And 1 plus a negative 2 is going to give me negative 1. These are going to be your final answers. So we have our r prime is at 1, negative 1. our S prime is going to be at 0, -3. I'm going to move my label for my R prime so it's not in the way. And then our T prime is at -3, -1. And then this is going to be our final answer. So there are more steps to it when you're rotating around a point, but that's because you have to move it in order for your rules to apply. If you do not move it and you go straight to using the rules of rotation, you do not get the correct answer. So using example 4 as guidance, I want you guys to go ahead and pause the video and try example number 5. So on example number 5, I want to start by figuring out what those coordinates are that they gave me. So this point here is over 1, 2, 3, 4, 5, 6, and up 4. This point here, they go over 3 and up 6. And then this other point, we went over 6 and up 2. Okay, so this time they're not giving us labels on points, they're giving us the points and testing our ability to then list those points. So we are starting with 6, 4, 3, 6, and 6, 2. So because I'm rotating 90 degrees counterclockwise about a point, I'm rotating it around the point -4, -2. I need to start by thinking of a translation vector that would move me back to 0, 0. So all of my x's need to go to the right. 1, 2, 3, 4. And all of my y's need to go up 1, 2 in order for our rules of rotation to take place. So I'm adding 4 to my x's. And adding 2 to my y's. Okay, so I have my points. Oh, and I do want to make a correction. This was a -6, which changes my answer. I want to catch that, double check that before I start the rules of rotation, because once I rotate, it's hard to get back. So -6 plus 4, this should actually be a -2. Okay, so now that I've moved all of my coordinate points, I want to use the rule of rotation. So my rule of rotation, if I'm going 90 degrees counterclockwise, my x and my y's switch positions, and your first coordinate is going to change signs. So our first coordinate, which is now -2, 6, they're going to flip. So this is going to be 6, -2. And then our first coordinate is going to change signs. So this is going to be -6, -2. Our second coordinate that went from being 3, 6 to 7, 8, we're going to flip them, your x and your y. So my 8 is now my x coordinate, and my 7 is now my y coordinate. And our 8 is going to change signs. My last coordinate, my y was 4, so now that's my x. My 10 was my x, so that's now my y. And my first coordinate is going to change its sign, so that is going to now be a -4. So I moved my points. I rotated them using the rules of rotation. Because I moved it, I have to put it back where I found it. So in order to put this point back where I found it, I added 4 to all of my x's, so now I need to subtract 4 from all of my x's. And since I added 2 to all of my y's, I need to subtract 2 from all of my y's. So -6 plus a -4 gives me -10. And -2 plus a -2 is going to give me a -4. Negative 8 plus a negative 4 is going to give me a negative 12. And 7 plus a negative 2 gives me 5. And our last coordinate, negative 4 plus a negative 4 gives me negative 8. And 10 plus a negative 2 gives me a positive 8. These are going to be my coordinates of all of my images. So negative 10, negative 4. We should have a point down here. We have a point at negative 12, positive 5. And a point at negative 8, positive 8. So my green image is now my image, and the black one that was provided is my pre-image. Okay, again, go ahead and pause the video and try example number 6. So on example number 6, we need to figure out those coordinate points first so that we know what we are rotating. So we have a point here at 0, 4. We have a point here at negative 5, negative 2. 1, 2, 3, 4. Sorry, negative 4, negative 2. Wanted to double check that. And then the last one, we have a point at negative 6, positive 3. So you should have started by moving your point to the origin so that you can use the rules of rotation. Since it was a positive 5, 0, I know that I can negate both the 5 to be a negative 5, and the 0 would just be 0 because that can't be negative, and that would create my translation vector. I'm then applying that translation vector to your coordinate points. So 0 plus a negative 5 is negative 5, and 4 plus 0 is 0. Negative 4 plus a negative 5 gives me negative 9. And negative 2 plus 0 is negative 2. This should have been a 4. That's why we catch our work now. We check it as we go along. So negative 6 plus a negative 5, I should have got negative 11. And 3 plus 0 gives me 3. I then need to apply the rule. But I notice that this says 90 degrees clockwise. So since my rules apply counterclockwise, I need to think about what 90 degrees clockwise actually is. So 90 degrees clockwise, if I had a graph, and let's say here's my point, 90 degrees clockwise would put me here. So if I want to go counterclockwise, that would be 270 degrees. So I'm actually using the rules for the 270 degree rotation instead of the 90 because it'd be 270 counterclockwise. So your X and your Y are going to switch positions, and your second coordinate is going to change signs. So my X and my Y flip. This becomes 4, negative 5, and then I change the sign on my second coordinate. Again, flipping my X and my Y and changing the sign of the second coordinate. Apply that to all 3 points. And now we have the points after their rotation. So I moved my points so that I could rotate. I need to be sure that I move those points back where I found them. So I need to add 5 to my X's and then do nothing with my Y's. So positive 4 plus 5 gives me 9. And 5 plus 0 gives me 5. Negative 2 plus 5 gives me 3. And 9 plus 0 is 9. 3 plus 5 is going to give me 8. And 11 plus 0 is 11. My last step is to go ahead and graph these points. So I should have a point here at 9, 5. I should have a point at 8, 11. And a point at 3, 9. And here we have our pre-image. So pre-image is our blue, and our image, which is our green. Okay, we're also going to cover 3.5 today, which is just symmetry. So this is something that you should be familiar with. It should be a review from 8th grade, which is why I think that we can go ahead and just kind of give it a quick review. So symmetry is if a rigid transformation maps a figure onto itself. So this would be your translations, your rotations, your reflections. Line symmetry, which is also known as relation symmetry, is if a figure is mapped onto itself through reflection, and line of symmetry, also known as the axis of symmetry, is the line of figures reflected over if symmetric. So this is kind of like when you were in kindergarten and you would fold a piece of paper in half before you would cut out your heart so that you would ensure that they were in fact symmetrical on both sides, that both sides looked the same. So for example 1, it states whether the objects appear to have line symmetry, and if so, to draw the lines of symmetry and state their number. So go ahead and pause the video and complete example 1A, B, and C. So on example 1A, I see one line of symmetry straight down the middle of my crab. For B, there is a line of symmetry through every point on your star. So through every point, because this is a regular figure, through every point, I have a line of symmetry. So since I have 5 points on this, I have 5 lines of symmetry. And then on C, I don't have any straight up and down, but I would be tempted to try a reflectional symmetry through the diagonals, since this is a rhombus. If I reflected this over, though, my point would end up here, and this corner would end up here, so that wouldn't work. So in this case, there are no lines of symmetry. So this would only work if my sides were congruent to one another. So that's line symmetry. Rotational symmetry is if a figure can be mapped onto itself by a rotation of 0 to 360 degrees. So it has to map onto itself somewhere between its start and its finish. With rotational symmetry, we have the center of symmetry, which is the point which the symmetric figure rotates around. And when we're looking at rotational symmetry, we're trying to figure out how many times that figure is itself when rotating around. So it's like when you were a kid, There's that toy that it's the blocks. It's a giant cube that you try to put figures into. You have like stars and octagons, and you're trying to make sure that it fits into the hole. That would be our order symmetry. So it's the number of times a figure rotates into itself. As it rotates from 0 to 360 degrees. So it goes in a full circle before determining how many times that happens. And then the magnitude of symmetry is the smallest angle a figure rotates to map onto itself. And the easiest way to do that is by taking the 360 degrees and dividing that by your order, or the number of times you can map it onto itself when rotating around a circle. So on example number 2, I want you guys to go ahead and pause the video and determine how many times this figure is itself when turning it in a complete circle. So on example 2A, we have a flower. And I notice on this flower that each petal is a little bit different from one another. Okay, so since each petal is a little bit different from one another, there's actually no rotational symmetry. It doesn't matter what degree I switch this in, because each petal is different. It never is going to be the exact same. On example 2B, we see the recycling symbol. So I know that since those are all the exact same figure, it's just mapped out 3 times. My order here is 3. If I rotate this 1 time, it's still the same figure. 2 times, still the same figure. 3 times, still the same figure. Which means that if I wanted to find the magnitude, I would take 360 degrees divided by 3 to figure out how many degrees I have to turn it before it's the exact same. So in this case, if I rotated my figure 120 degrees, it's the exact same. So if that was a hole and I needed the figure to fit into the hole, I would only need to rotate it 120 degrees before it would fit. For C, we have a snowflake. And we know it's like a cartoon snowflake because we know all snowflakes are different from one another. So I know that if I rotate this the slightest bit, these two are the exact same figures. So as a result, every time I flip it, it's then creating the exact same figure because these are all the same, they're all congruent. So I can rotate this 6 times within one full circle, and it is the exact same figure. You wouldn't know that I would have rotated it because when you switched it, when you looked at it the first time to when I rotated, it's the same. So my magnitude in this case, I'm taking 360 divided by 6. This tells me that I have to rotate this 60 degrees before it's the exact same figure again. Okay, this symmetry also can apply line and rotational in a coordinate plane. So on example 3, it says state whether it has line symmetry and or rotational symmetry. And if so, describe the reflections or rotations. So like on example 3A, I noticed that I have a rectangle. So because it's a rectangle and the 2 sides have the same slope on your opposite sides, I can look at the length of the top of my figure. So the length of the top of my figure is 1, 2, 3, 4, 5, 6 units. So if I split that in half, I would have a line of reflection there where that figure, if I fold it across that line, is going to map onto itself. So I have line symmetry through that point. So this happens at x equals -1. It also happens here across this line, where if I were to fold it along this crease, because there's 4 units across this top and 4 units across this bottom, that there would also be the same amount on both sides. So that line is going to be y equals 0. I then need to figure out if this has rotational symmetry or not. So based on the line symmetry that I just found, I know that this is going to be the center of my figure. So if I flipped this figure once, my rectangle is laying on its longest side, so that would not be congruent to its original figure. But if I rotated this twice on its side, you would then see that it does have rotational symmetry. And that's happening around the center, which is at -1, 0. And it happens every 180 degrees. Okay, go ahead and pause the video and try example 3B. So on example 3B, I noticed that the top of my figure and the bottom of my figure have 2 different lengths. This is 4 units. Sorry, this is 3 units. And the bottom is 4 units. Because that's the case, this is going to have no line symmetry. And then because those are not the same and my 2 side lengths are not the same, I know that I'm also going to have no rotational symmetry. So I have no symmetry at all here. Okay, go ahead and pause the video and try example 3C. On example 3C, I noticed that to get from the corner to the top of my figure, I'm going up 1, 2, 3, and to the right 1, 2, 3. From here, I'm going up to the 1, 2, 3, and to the left 1, 2, 3. So these have the same slopes. These both have a slope of 1, which tells me that those are going to end up being the same because this falls directly in the center. I have 3 units on the left and 3 units on the right to get to those 2 vertices. So I have a line of symmetry, just one, through that line. So that line is going through the point -1. So I have line symmetry at x equals -1. And then since this bottom line is longer than the 2 sides, I know that there is no rotational symmetry. Okay, go ahead and pause the video and try example 3D. So on example 3D, the top of my figure is not the same length as the bottom figure, but they are parallel to one another. So I noticed that the top is 3 units and that the bottom here is going to be 5 units. So I know that the line that splits them in half would go through this point here. And then I would want to check the slopes on both sides. So from that vertex on the left, I'm going up 1, 2, 3, 4, 5. And I'm going to the right 1. So here my slope is 5. And I want to be sure on the other side that I'm going to have that opposite slope so that I know that they're going to be the same distance to get from the vertex to the top of my figure. So I go up 1, 2, 3, 4, 5, and I go to the left one. So this is a -5. I know that these are then congruent on both sides. This tells me that I have line symmetry occurring at x equals 2.5. And then I check for rotational symmetry, but because the top is shorter than the bottom of my figure, I have no rotational symmetry. Okay, I know that this was a longer lesson, but you do have homework on both sections tonight. So be sure that you are completing both sections of homework here. You should be completing page 243, number 13 through 15, as well as 19, 20, 27, and 28. And then you are also completing page 263, 27 through 30. If you have any questions, either post it onto our class